that big of a difference, but this one I think it does. Okay, let's switch to here. Okay, there we go. All right, so let me see. Okay, this is all good. All right, so first thing is I want to show you guys where we are in terms of the class material. So this way you can tell, which part we are at and what we'll be talking about after this week. So as far as we are concerned, we are close to being done with this entire module. So for today, I'm opening up the new lab, which is this one here, Simple Branching and Code Analysis. It's due in a week, and this one might take some time to get it done. So if you cannot get it done within the lab time, don't be surprised, because this one does get a little bit more, it needs a little more time. But it's also important to get through this one kind of slowly and understand all the material, because it really lays the foundation of all the other stuff that we'll be talking about after this section. So we'll do a quick preview of what we'll be talking about after all of this stuff here. So this is what we'll be talking about basically to the end of the semester. I'm turning all of you into C compilers. That's what I'm going to do. Okay, so you'll be given C code and translate C code into the assembly code, the mnemonics that we have been talking about. So that is basically what we'll be doing until the end of the semester. By the end of the semester, we'll have homework assignments that might have to do with structures, linked lists, and stuff like that. And before anyone complains and go like, but CISP430 is not a prerequisite of this class, don't worry, I'll give you the C code. Your job is to translate the C code into assembly code, okay? So it's not like you have to invent or you have to start with, writing your own C code to deal with linked lists, trees, and whatnot, but you do have to use my C code to translate it into assembly code and have everything running in the simulated processor. Okay, so we won't be dealing with large, complex data structures, but binary trees we can do, linked lists we can do, and so on. So we can do a certain degree of data structures even in all assembly language code. So that's kind of the map of what we're going to do. There's this one little executable here called hack1.stripped. We'll talk about that after we are introduced into the stack and what the stack is storing. Basically, it's an example of what you can do with exploiting Stack Overflow in a program. So that's like very simple hacking techniques with that particular sample program. So hopefully we'll get to that part because it's really fun. It doesn't have to do with TTP. It actually makes use of an executable that is using the 64-bit instruction set of the Intel/AMD processors. So it's actually kind of cool to go through that process. All right, so that's the map of what we'll be doing in the near future, basically until the end of the semester. What we'll be doing today is to focus on the things that you will need in order to get this lab done. Okay, so this lab is going to introduce a few instructions. Some of those instructions are fairly easy to follow, and some of those instructions are, well, a little bit trickier. So what we'll do is we are going to get Logisim started. And this time I have to be careful which one I'm using. Okay, this is the current one, so that's good. And then what we'll do is we'll write some programs using instructions that you have not seen yet. Okay, and I'm going to use this opportunity to demonstrate how those particular instructions work. And more importantly, it's just a replay of how to learn about the processor on your own. Okay, so let me go to the assembler sheet here, and we'll start with a program that is a little bit easier to do. So I'm going to start with a program that is not the one that we did that I did yesterday. So we'll start with a new one. So this way the two classes are slightly different, which means if you want to learn what the Monday, Wednesday class learn, you can actually watch their video too. So that would give you like kind of double exposure of the same material, just presented slightly differently, which can be good. Okay, so this is JMPI L1. Okay, and it complains unresolved reference, which is fine. Okay, because I'm going to define the label late after this. And then we have a halt instruction here. And then at L1, we have another halt instruction. And now we do not have any unresolved references. Okay, so this program doesn't seem to do much. The only new instruction introduced here is the JMPI instruction. So now the next question is, what does the JMPI instruction do? So if I were to say, tech is being extremely lazy, you guys just go learn this by yourselves, what would you do? Where's the dean's office? I'm going to complain, right? So what if the dean says, well, if tech says you should be able to learn this by yourself, you should be able to learn this by yourselves. Then what do? You try to find out who's the supervisor of the dean. You keep going up the ladder until somebody listens, right? But let's say that doesn't seem to be a viable option, okay? Because your job here is to learn, right? So how do we get started? Look at the opcode table, okay? So the opcode table is actually quite useful. So when you look up the opcode table, okay, let me magnify a little bit because we do want to focus on one particular instruction in this case, which is the JMPI instruction. So this is how it's described, okay? You can see the opcode is a fixed bit pattern. It doesn't change. There's no use of any registers within the opcode itself. It is simply 4-0. That's it. Okay? But what does it do? Well, what it does in column C seems a little bit confusing. It says whatever the program counter points to will go back and be stored in the program counter. So it dereferences the program counter, and then whatever is at the location the program counter is pointing to is stored into the program counter itself. Okay? Do we have any questions about what this is representing? It might be kind of confusing, but do we have any questions of what it is representing? Yes?
So we're taking, all right, so does this have anything to do with, memory addresses?
Yes. So the program counter as a register is used as an address. Okay? You go to RAM, you go to that particular location, you retrieve the content at that location. Okay. What do you do with that content at that location? You store that content back into the program counter. That's what this C notation is trying to tell you. Okay? So now that we have a vague idea of what it's doing, the next thing we do is we assemble the program, which is on my assembler tab. There's no error whatsoever. We can now go to the RAM file. And by the way, you can only download the RAM file from the RAM file tab. If you download from any other tab, it doesn't work. So you go to download, go to CSV. TSV will work as well, but I just typically use CSV. Save the file, and I'll call this jmpi.csv just because it is a program to illustrate what JMPI does. So now I switch back into LogicSim. Control R to make sure everything is reset. Right click on RAM, go to load image, and then specify the content, which is in /temp/jmpi.csv. And now we have that rather simple program loaded here. Okay? So we can now start the execution of this program. You can see the first instruction is a no op, okay? And you might ask, why do we start with a no op? Well, the reason why we start with a no op will be explained later, okay? But the first really useful instruction is the jump instruction itself. And you can now see that we are still in the fetch cycle, which means we are about to have a rising edge when the microcode pointer is at location 0. So once again, this is called fetch. Okay, we're trying to get the opcode from RAM into the instruction register. We good? Okay. So if I Control T, you will see the instruction register now has 40. The falling edge is going to update the microcode pointer, so it points to the next location. Nothing really important is happening. We're just moving on to the next slice of microcode. So I use the word slice in content in ROM kind of interchangeably because the individual locations of the ROM, each one specifies a very unique operation that you need to perform in order to implement instructions. So I call it a slice as in a slice of time. Okay. So now we are moving on to location 001. We are about to have a rising edge clock. This rising edge clock, all it's going to do is to update the program counter. So the program counter is going to increment. Normally, that operation doesn't seem to be very particularly useful because all we are saying is, yep, the opcode at location 01 is now stored in the instruction register, so I don't need to point to that location anymore. I'm ready to point to the next location. So normally, it doesn't seem to be very important, but this time, it is important. So let me do a Control T first. So now it points to location 02. If you look at the program counter, which is right here, it is now pointing at location 02. Big deal, right? We just grab the opcode at location 01 and the program counter now points to location 02. But what is at location 02? That is the question. You can go to the RAM content and find out what is at location 02. It shows you that at location 02 we have a 04 there. But it doesn't tell you what it is, okay? It doesn't tell you what it's for. So the best way to find out what is the meaning at that location, is to go back to the assembler and go to the assemble tab. The assemble tab gives you all the kind of like the X-ray vision of the program. So when you look at this particular one, we want to find out what is at location 02, right? Because the program counter is now pointing at location 02. Can someone tell me how do we find out what is the content at location 02 using this particular tab? It's one of the first few questions, like the second question of the first lab that has something to do with a text toy processor. Do you remember? No? Column W tells you the location. Column X tells you the first byte starting at that particular location. And if column Y has something, it tells you the byte after the first, it would be the second byte from that location. Do you vaguely remember that one? Because a lot of people ask me, where's location 08? Remember that one? Yes, hopefully. If you don't, I'm worried. I'm really worried if people say, no, I do not remember that at all, okay? So 04, okay? This 04 is at location 02 because the 40 is at location 01 and this memory is byte addressable, which means each byte has its own address. So 04 has to have its own address, which means it is 1 after 01, and that makes it 02. Is that okay? So what is this 04 representing? If 40 is the opcode of JMPI, what is 04? So you look, yeah, go ahead. There was a L1, exactly. So when you look up the definition of L1, which is on line 4 or row 4, you just keep looking and you can see that L1 is defined to location 4. Now, if that is not enough to convince you that L1 has a value of 4, you can go to the symbol table. So in this case, the symbol table only has one label, which makes it really easy to read. So it says L1 is defined on line 3 because we start counting from 0. It has a value of 4. Okay? So you can double check, how a label is defined by going to the sim tab, symbol table tab or sheet. Okay. So what is the big deal? Well, the big deal is this is where the pointer is pointing at. And according to the opcode table, we are going to where the program counter is pointing to and retrieve the byte pointed to by the program counter and then store that into the program counter. So in this case, that would be 04, okay, because that is what the program counter is pointing to at this point. Are we good so far? Okay. So understanding what the processor needs to do, now really it's just a question of tracking down, all the multiplexers, demultiplexers, enables, selects, and whatnot to make sure that that does happen, right? So what we do is now we go to the ROM and we say, let's decode it. The falling edge, when the microcode pointer is at location 001 and you're having a falling edge, that is called decode, because that is the instant where we grab the instruction register, pad 4 zeros to the right-hand side in binary, so that the microcode pointer becomes the most significant 2 digits would be the same as the instruction register, but then we have a 0 padded to the right-hand side. Okay, so that's called decoding because we are looking up a table, which is our ROM, to find out exactly what do we need to do with this specific opcode. Yes?
And when we're at 0, it's called fetch?
When we're at location 000 on a rising edge, it is fetch.
Okay.
So location 000, rising edge, it's fetching. Location 001, falling edge, it is decode. Okay? And in between those two steps, they don't really have a particular name, just auto-incrementing the program counter and also auto-incrementing the microcode pointer. So they don't have any specific names. All right, so another control T, and not surprisingly, now we are at location 400 in ROM. So now we need to go through the analysis. So this is what you need to do if I introduce a new instruction and I don't tell you how it works. This is what you need to analyze in order to find out how the opcode gets the job done or what it does, okay? All right, so the analysis starts with, I'd like to start it with RAM because if RAM is selected, I have a whole bunch of questions to ask, and those will lead me to a lot of answers. So I like to start with RAM. In this case, RAM is selected, okay, because RAM cell is a 1, and when RAM is selected, it's paying attention. Next question, are we reading or writing? Load is 1, we are reading, okay? So now the natural question is, which location are we reading from? Well, the highlight tells you that, okay? But the question is, what is telling the address port that we want to look at location 02? Now, we already know because we talked about it, like the program counter is used as a pointer, but it doesn't hurt to double check, okay? So what we do to double check that is we track down the address port and say, who is driving the address port? This multiplexer is driving the address port. Well, a multiplexer has 2 inputs, so which input connects to this particular output? The select is 1, which means input 1 is used to drive the output of this particular multiplexer. And input 1 goes to the output of the program counter, and no other output is connected here. So there's no question of who is driving this particular wire. It has to be the program counter. So the program counter is connected through a multiplexer to the address port of RAM. So this is why we say we are dereferencing the program counter. When you encounter when you encounter the unary operator asterisk in a C and C++ class, which to you it means dereferencing, that means whatever you're using to dereference, which has to be a pointer, is driving the address port of RAM. Is that okay? So I want to kind of link those two concepts, dereferencing from cisp310 to driving the address port of RAM in this class. They are basically the same thing. Are we good? So now what is the content? What is the data port outputting? Well, it's just the content at location 02, which is, oh, guess what? It's just 04. No surprise there. The question is, where is it going? Okay, since I'm reading from RAM, I'm hoping that some component is making use of that content, right? So now I have to track it down, okay, and ask, okay, who is paying attention to the address port of RAM? Quite a few things, okay. The instruction register here is not paying attention. Okay, fine. We look at the register bank, and the register bank also has input enable turned off, which means the register bank is also not paying attention to the address port of RAM. Then we get to this multiplexer. Okay, we want to see where this multiplexer is going. This multiplexer has a select of 1, and this is in fact input 1. So now we say, well, we better track down where it's going. This wire connects to input 1 of the other multiplexer, and the other multiplexer also has a select of 1, which also means we better check what it is connected to, and turns out it's connected to the input of the program counter. Not only that, the program counter also has program counter enabled being a 1, which means on the next rising edge, the program counter is going to update based on what it is seeing in port D. Are we doing okay so far? So are we convinced that something really strange is going to happen, which means the program counter is driving the address port of RAM. What we are retrieving from RAM is now going back to the input of the program counter. So when the program counter sees a rising edge at the clock, it will update to the content that it is pointing to. So are we convinced? Yes? Okay. So we do a Control T, and we see the program counter updating to 04. Okay? So that is kind of cool. All right? So the next thing is, what are we doing next? So now we're going to have a falling edge. The falling edge only updates the microcode pointer, so nothing else is going to do much on this falling edge. But according to this multiplexer has a select of 1, which means we're tracking down input 1, which is just incrementing. So that means the microcode pointer will increment to location 401. 401 only has the most significant bit of the entire bit pattern being a 1, which is this bit here. When this bit becomes a 1, this OR gate will output a 1, and that 1 in return will reset the microcode pointer back to location 000, so we'll be ready to fetch the next opcode. At which location? Well, which register tells me where to fetch an opcode? The program counter. Okay, the program counter is telling us where in RAM we are going to get the next opcode. So based on what we just did, okay, I know we are not showing the program counter's content at this point, or it's just barely showing. But based on what we just did, do you remember what is the value of the program counter at this point? 04. Very good. So that means the next fetch is going to go to location 04 to retrieve an opcode to execute. Okay? So what is at location 04? If we go back to the assembler and the assemble tab, we can go to location 04, which is here, right? Because column W tells us the location. So location 04 has a content of 01, and that does correspond to the halt instruction. So that's where we're going to go. Is that okay? All right, cool. So we go back to the simulator and we just kind of Control T a few times to make sure that is going to be what is happening. So I scroll up a little bit, you can see PC is 04, Control T, da 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 da. Okay, now we are stuck because the halt, that's the job of the halt instruction, is getting stuck. Okay, it's not going to go anywhere from here on. Are we good? Okay, so it is when you're introduced a new opcode, going through this exercise, clock by clock, edge by edge, is important because that is how you study for this class. Okay, how many instructions do we have? You go to the opcode table and you say, okay, some of these are not implemented, so you don't have to worry about those. Do you think you have to study for this particular opcode? That really is just a fetch, okay? So no op is really just the fetch operation that you have to do for every single instruction, okay? Because it fetches, but then it finds out it has to go back to location 0, 0, 0. So it doesn't do a single thing, but it does advance the program counter because location 0, 0, 1 on the rising edge increments the program counter. So no op, unlike halt, does increment the program counter so they can get to the next opcode in memory. Okay? The next one, halt. I think we have explained enough times about what halt does. It's not even funny to talk about it again anymore. Okay? Moving on. We just talked about JMPI. Okay? So no big deal. And then there's a whole bunch of J blah blah I. Okay? Those are conditional branch instructions. So these are, okay, if you look at what the C notation says here, what is the question mark doing here and what is the colon doing here? Isn't that syntax error in C?
Ternary if, I believe.
Yep, it's called a ternary operator. So I'm glad that a few people in this class, remember it is called a ternary operator. It is it's a conditional statement in an expression, basically. Okay. The question, whatever is to the left of the question mark is the condition. Whatever is between the question mark and the colon is the then value. Whatever is to the right-hand side of the colon is the else value. So evaluates the condition. Depending on whether the condition is 0 or not, it will return the entire expression. Will either use the second expression as its value, as the then value, or it would use the third expression after the colon as the else value. So it's basically an if then else in a single expression. Okay, quite useful. So when you look at JLI, okay, in this case, what is it doing? Well, it's looking at the L flag. Now, if I just say L without L equals 1, it's the same thing. Okay, I do not need to say L equals 1 because L is Boolean. Okay, if L is true, then I return whatever the program counter points to. Wait, we just did that, didn't we? The JMPI instruction is doing exactly that so that we know where we are going to. So now the question is, what if the L flag is not set? What if the L flag is a 0? It just says, well, just move on, go to the next instruction. That's all it does. But this mechanism is how we make decisions in assembly language, okay, so that we can have a branch. Okay, if the carry flag is a 1, I want to go over there. What if it's not? Well, then we just go on to whatever is after the JLI instruction. Okay, so if you are presented with this entire family of instructions, are you going to single step or use Control T to go through every single one of these to understand how it works? You don't have to. Work out one, the rest are pretty much the same. They just look at different flags or different bits of the flag register. Okay, so I would consider these as kind of one group of instruction. Doing Control T, step by step. Once for one of these is probably, well, I have to do it twice because you have to do it once when the flag is a 1 and you have to do it once with the flag is being a 0. Okay, so that you can see how the processor circuitry can differentiate and behave differently. Okay, so that's one thing that you probably want to do because this is a little bit more complex instruction. But if you track down the logic of Logisim, of the processor in Logisim, you should be able to figure it out. Okay, CPR, okay, which has nothing to do with helping to revive someone. CPR stands for copy register. Okay, so copy register, all it does is to copy register Y to register X. Okay, not exactly difficult. Okay, because all it does is to do something with the register bank. Select one of the registers as the output of the register bank, route that back to the input of the register bank, and select possibly another register to update. Does it make sense? Okay. Okay, so this one you can probably track down just like that and understand how it works. We are not going to talk about the JL without the I. So when you use these instructions, make sure that you use the one that ends with an I and not the ones that do not end with an I. Okay, so we'll basically not pay attention to these instructions, and there are two more down there somewhere. This is LDI. I think, did we talk about the LDI instruction? Okay, so we're done with that. And you can see the LDI instruction has some resemblance to the JMPI instruction. The first one is they both end with an I. That I stands for immediate. The second one is they both use the program counter. They both dereference the program counter. See how LDI dereferences PC++, and the other one dereferences your PC. The only difference is one would do the dereference, then increment, and the other one just dereference, does not increment after the fact. That's the only difference. Okay? So when you notice these similarities, then you will start to understand the processor and how it works in general. This is the LD instruction. Okay, so we have a whole bunch of computational instructions, which is going from 26 to 29, and then there's one more, somewhere else. Two more. So we have add, we have subtract, we have right shift, we have not, and then we have bitwise AND, bitwise OR, and then compare later on. Okay, so this entire family of instructions, each one, okay, if you look at add, there are 16 variations of add, because you can add A to A, you can add A to B, A to C, A to D, then you can add B to A, B to B, B to C, B to D. So there are 16 variations. Are you going to single step all 16 variations to understand it? No, one is enough, right? And if you look at all of these instructions, add, subtract, right shift, not, bitwise AND, bitwise OR, just doing one is enough, because they're just going through a slightly different path inside the ALU. So I would just do add and subtract, because the other ones are actually simpler in many ways. So that collapses the number of instructions you have to, single step through in order to understand the processor significantly. Okay, JMPX is something that you do have to understand, but if you look at the C notation, does that look really difficult to understand? Pick one of the four registers, A, B, C, or D, copy that to the program counter. I mean, all you have to do is to figure out which multiplexer to configure and which demultiplexer to configure, which register to enable, and so on. So you can do it in reverse, right? I mean, you can look at this and you ask, how do I implement this? Which multiplexer is in use, which demultiplexer is in use, and for each one that is in use, how do I switch the input or the output to accomplish what we need to do? Is that making any sense? Okay, so you can do it in reverse. You can look at this and figure out the pattern of how you have to configure all the multiplexers and demultiplexers to implement the instruction, instead of looking into the simulator to find out how it is implemented. Okay. Oh, these two are the escapees. So you can kind of ignore JC and JZ, because we are not going to use those instructions. They do exist, but we're not going to use it in this class. And then we have these two. We talked about these two already. And or and even compare. They are less complex compared to add and subtract, because there's no, except for compare. But with and or, there are no overflow, to consider. So they're actually simpler instructions. ST is the reverse of LD. So if you understand LD, you already understand ST. And then we have the increments, okay, increment and decrement. Those are kind of interesting. So I would at least trace through one of them, okay, because one goes through the adder and the other one goes through the subtractor. The one thing that you want to kind of find out is, how come the flex register is not updated by increment or decrement? Okay, so you might want to track that down, by executing the instruction, use Control T to single step through the whole thing. And when it's about to do the calculation, check out the logic and see how the flex register is disabled, even though the ALU itself is enabled and performing an increment or decrement. Okay, so this is how I would envision you to study and understand the processor. Okay, Now, if you go through this process and you go like, well, I'm stuck here, I can see the simulator is doing this, but I don't quite understand how it's getting the job done, I'll be more than happy to answer those questions, okay? But you have to kind of do some of the work in order to gain a good understanding of the processor and how it works, okay? So this is kind of at a micro level. We are looking at the microcode and try to understand how the microcode is implementing the opcode. After this, we'll be focusing only on the opcodes. So we're not going to getting into the details of the microcode because we want to implement C programs. I cannot be talking about multiplexers and demultiplexers all day long because that's too low level. Okay, so at a certain level, we're going to have to talk about just the opcode and not getting down to the microcode. All right, so getting back to more tools to help you figure out how your program executes. Okay. So let's go back to the program that we just did, okay? I'm going back to here. And I have to make sure the clock is low before I reset just the processor. So if you click this button to reset the processor, when the clock is low, you don't have to clear the RAM. In other words, I can keep RAM content exactly the same and then just rerun the program from scratch. Is that okay? So, but if I want you to tell me, what is the path of execution, when the program runs like this, it's extremely tedious because what you need to do is you have to keep track of the program counter. The program counter is all the way here. So you have to keep track of the program counter and observe how it is changing over time. And that's really tedious because as you control T, you have to keep an eye on the program counter. And you also have to go back to the assembler to find out, okay, which location is the tricky one and I better stop, when I get to that location. So it does make debugging a program really tedious because you have to do Control T. There's no breakpoint in this processor. You cannot just say, I want this whole thing to stop at location blah. Doesn't work that way, okay? So you might think debugging a program using this processor is going to be super difficult. Well, I'm giving you extra tools, okay, to make that simpler. So the extra tool that I'm giving you is documented already. If you go to the assembler manual, which I hope many of you have at least checked it out, even if you have not read it from the first page to the last. But there is one section that talks about debugging. So assemble, how to debug. There we go. Okay. So this is the section that will give you a tool to help you analyze the execution of a program. I do want to make it clear, okay? If anyone does not want to learn this, it's okay. I'm not going to ask direct questions about how to use this technique to debug a program, okay? All I'm saying is this can be a very useful tool to help you, one, debug a program, and two, to understand the material from this point onward, okay? So it's a tool. It is up to you to decide whether you want to learn how to use it or not, okay? I'm just saying that it is available, okay? There's the availability of this tool, and I'll show you how to use it. But if someone says, this is too complex, I can do better just by Control T or using my other techniques, I'm not going to stop you, okay? All right, so that being said, now we go into the details of how to do this debugging. And I'll show you, okay? I'll show you today how to do this because you might find it useful even for this particular lab, okay? So we'll go ahead and take a look at this tool. The first thing is you have to get the jar version of Logisim. So if you already have the exe, fine, keep the exe version, but you will also need to download the jar version of Logisim, because you will need to run Logisim from the command line. All right, so there are a few pieces you need to know where to find those things. The first one is, where did you put your Logisim blah 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 .jar file? Okay. The second one is, where did you put your processor 0003.circ file, which you should have already, just to do the homework assignments up to this point, but you need to know where it is in terms of the file path. The last one is the program that you want to run, which is the content of RAM. You also need to know where you put that, okay? So there are 3 files that you need to know where you put those files, or what folders you have put those files into. And this one is the output. You can put it anywhere, but you will need to find where it is in order to upload it and use the trace analyzing tool. So there are 4 files involved. So I will go ahead and rerun this program using this tool. Now this tool is command line based, which means you just go to the command line, and I have the earlier versions already, but I'm going to retype the whole thing from scratch, just so that I can talk about the whole thing and kind of show you where how you can type your own command. So I am typing everything from a folder that is not where I put any one of these files. Okay, so I say java-jar. Okay, this is a switch to the Java interpreter to say okay, run everything from this Java archive file. JAR stands for Java archive. And then I specify the path to my logisim.jar file. And if I remember correctly, it's my home folder, document cisp310, and then it should be there. There we go, okay? The next one I need to specify is the circuit file, which is the processor file. So that one, I think I got it in my documents, cisp310, processor as a subfolder, and then processor 0003.circ. Okay, so that takes care of this one. And then we have a switch of -tty. TTY stands for teletype. It's basically a switch to tell the program, Logisim, not to start up the GUI, not to start up the graphical user interface, because we want to stay on the command line, have everything basically being done automatically in batch mode. So that's why we have a -tty. But after -tty, you have to specify a word. And in this case, I think the only one that makes sense is table. It's going to generate a table, basically a spreadsheet of some kind that will give you kind of like an idea of how everything works, or what happened during the execution. -load is telling Logisim to go to a particular place to find a RAM file, okay, which in this case would be my /temp/jmpi.csv, which is the same file that I load into RAM earlier using the GUI method. So that would be /temp/jmpi.csv. Okay, so this is done. Okay, this is the entire thing. You can run it just like this, but the output of this is not going to be very helpful. Okay, because this is basically the output of all of the output pins. It's capturing all the output pins in a particular order. If I remember correctly, it's from top to bottom. Okay, so that's why I told you guys do not move the location of the output pins. You can move everything else, but not the output pins, because if you move the output pins, the ordering of these things would change. So every time something changes, every time if at least one of the output pin changes, it creates a new row to tell you the state of every single output pin in the processor. Is that okay? That's a lot of bits, a lot of zeros and ones. Yes?
Do we have to set up the processor with the ALU in the register bank before we do this?
So this will basically go from the reset state of the processor, and you cannot pre-plant a value in the register. So if you want to start with specific values in the registers, you will need to use LDI to load a specific value into the registers.
No, what I was asking was you only, in this command line, you only do the path to processor 3.
Mm-hmm. The other two, okay, so I see what you're asking. So when you specify only the location of the processor 0003, if this is the first time you do it and the circuit file does not know where to find ALU or the register bank file, it will give you a it will give you a dialog box to say where are those. but it won't be able to save it because that information, is saved with processor 0003.circ. So you will need to do this without the -tty once. Just write everything up to this point, but without the rest. Do it once, so that it would remember the location of the other two files. Then from that point on, you can do it this way, and it won't prompt you again because it would have remembered where to find those two files. Okay, so good question. Yeah, basically, it's going to be saved. But if you do this and it asks you, it won't remember it. So you have to do this with the GUI, without the -tty and the rest. You have to do it once so that it remembers. Okay. All right. So this is not very useful because I cannot decipher the output of this too quickly. So what I do is I redirect. Okay. Greater than on a command line, both in Windows and all Unix type operating system, that includes Mac OS X and Linux, is redirection. So redirection means now the output can go to a particular file. I just generally call that log.tsv, and I put it into the temp folder because there's really no need to keep it around after I reset the computer. So I put it into the temp folder. Now in Windows, you can put it into the same folder as everything else. Okay, this is my recommendation. If you don't want to type a really long path to each file, is to put everything into the current folder, and then use CD to go to that particular folder before you try to run this command line. But in Linux, this is what I usually do. So I press the Enter key, and it seems as if nothing happens because the output is captured into that file. So if I do a vim, okay, use any text editor and look at that file, I have everything back. It's TSV because it is tab separated value, not comma separated. So that's why I use the extension TSV. So you can analyze this file on your own, okay, and try to figure out things. But because everything is in binary, okay, it's really kind of a headache to look through that whole thing to look for certain things. So I have a tool that I have already quote-unquote developed that can make this process a whole lot easier. So this is the rest of the process. So you switch back to your browser, and then what you do is you go to the trace analyzer, which is in the same folder as the assembler. The name of that spreadsheet is the trace analyzer. So it already has some content in it. I'm not going to worry too much about it. So this is the steps, okay? The steps is you have to go to sheet 1 first, okay? So you have to go to sheet 1, go to file, okay? It's actually still doing some computation, so it's not responding. There we go. Okay, go to file. I just clicked on something else. Okay, there we go. Go to file, go to import. Once you get to import, you want to upload your TSV file. So you just select it from temp/log.tsv. Okay, then it will upload it, but it's not imported yet because it wants to find out how that file is supposed to be imported. Now this is the important part. If you get to this part here, make sure that you replace only the current sheet, okay? That this is important. And instead of using detect automatically, just say tab because we know that file is tab separated. And also select no when it comes to convert text to numbers, dates, and formulas. Okay, so make sure you use all of these options. And then you can click import data. It will take, not too much time because this trace is relatively short. So you will say, okay, now it looks better, but it's still a whole bunch of zeros and ones. So what you do is, I just mistyped something here. So what you do is you skip sheet 2, which is an intermediate spreadsheet for me to do some black magic in spreadsheet. You skip it to analysis, and this is cool because what this is saying is we get to location 00, we execute the instruction at location 00. Then we get to location 01, we execute the instruction at location 01. This part here is telling us in the process of executing the instruction at location 01, we read these locations in RAM. We read location 02, okay, see this little asterisk here? It means if you dereference location 02, it has a content of 04. That's our destination jump location. And when we read location 04, we have the content of 01. And you can also see in column A, it tells us that the last instruction that we execute is at location 04. So it analyzes the trace, and it basically it generates a summary of the execution of the program. And it will tell you if your program changes registers, it will be reflected here. If it changes any location in RAM, it will be reflected here. If any flag got changed because you have a register change, it will be reflected over here. Okay, so that can make debugging a program significantly easier compared to without this tool. Now, this tool is kind of what we call a post-mortem kind of tool, which means you're not using this tool while the program is running. You run the program through, then you use the log in this particular tool, and it will give you an idea of how the program executes. Is that okay? All right. So once again, this tool, may or may not be useful to you. Okay. Some people look at all the command line stuff and immediately say, no, I'm not going to use this. Okay. But the command line stuff can be made simpler. Okay. You can create a batch file, for instance, in Windows. Okay. So if you can fix certain locations of the files, you can parameterize just the name of one or two files. Okay. And then you can double click on the batch file or just run it on the command line, supply the actual changes of the file names, and you're done. Okay, you can, if not that, okay, the other way to make this simpler is really just to copy and paste this entire thing into Notepad. Save that file as a text file. Next time you want to do something like this, paste this whole thing, change a few things that you need to change, and there you go. Not quite as elegant as having a batch file, but it still saves you a lot of time not having to retype everything from scratch. So you can figure out what makes it easier for you to make use of this tool, but I am saying this tool can be very, very helpful as we get down to more advanced topics. Are we good so far? Yes? Okay. So with this tool, now we can play with things that will change, that will branch. Okay, so what we'll do is we go back to this program, and then we'll do something that will involve decision making. So we'll oh, by the way, to use that tool, the first opcode has to be no op. Okay, so it's safe to start with a no op, with every single program at this point. All right, so we'll do LDIA with a particular number. Okay, and I'll say K1, constant 1. LDIB with constant 2, and then we'll do a compare AB, and then we'll do a conditional branch. Which condition? Yeah, go ahead.
You said that this command requires a no op. Is there a reason why?
Yes, it is a bug of Logisim. So Logisim has some kind of a bug. If you use the GUI version, things get initialized correctly, and the first opcode would run correctly. But if you go for that option, using the -tty and not to use the GUI, for whatever strange reason, it is not initialized correctly. So the first opcode, executes in a funny way. But no op is okay. No op is not affected by that bug. So you want to start with a no op, and then all the subsequent instructions will execute correctly. Okay. All right. So after the compare, we can now do a conditional branch instruction. So we'll pick one of those. So you guys can pick which one do you want to use. We have the 5 flags. We have carry, 0, sign, overflow, or L, which is signed less than. Which one do you want to use? Pick one. Overflow. Okay, so we have a joy, J-O-I. Good choice. Okay, we like joy. And being INTP, having my mind, branching out uncontrollably. Right now, the image in my head is Joy of that movie, the Pixar movie, what, Inside Out. Yeah. So Joy from Inside Out is now popping in my head. It's like, no, Joy, go away. Sadness, come, take joy away. I like sadness. I think that's my favorite character in that movie. But then I'm getting distracted even more now. So JOI to L1, and then we have a halt here, and then at label L1, we have another halt instruction so that we can tell whether it branched or not, right? Okay. The program obviously is not working yet because K1 and K2 are not defined yet. So this is how we can make the program a little bit more parameterized, because now I can define K1 to be, do you want it to overflow or not? Okay, because we have to test it in both cases, once with it overflowing and once with it not overflowing. So which one do you want to go for first? Overflowing, okay. So this is a subtraction. We are basically subtracting K2 from K1. So how do we make it overflow? And we can only specify non-negative integers, okay? At least at this point, I have not, implemented the logic to deal with negative values. So let's see how we can make it overflow. We can make K1 the most negative number possible. And you look at this and go like, really? Is that negative? And K2 only has to be something that is, very small. Okay, so I claim K1 is the most negative value that you can store as a 8-bit signed number. Would you buy that? It just looks weird, right? Because what is 128? 128 is, go ahead.
127.
Is 1 followed by 7 zeros. Very good. So when it comes to the binary representation, 128 is represented by 1, okay, which is bit 7, followed by a whole bunch of zeros. Those will be bit 0 to bit 6. Using the signed interpretation of these particular bits, what would be the interpretation of these bits if I choose to interpret the bits and see them as a signed number? Negative 128. So that's why, when I say 128, it really is the same thing as negative 128 because this processor is 8-bit wide. Okay? Is that okay? So I'm hoping this is okay because this is a conceptual question, okay? Differentiating the value from the representation. And also, we also have to kind of take into consideration what is the signed versus the unsigned representation. 1 is just 1, which is a whole bunch of zeros on the left-hand side this time, and having bit 0 being a 1. Okay? So I claim this is going to overflow because negative 128 minus 1 is supposed to be negative 129, which cannot be represented as an 8-bit signed number. Okay? If anyone is thinking, when did we talk about the range of signed values versus unsigned values? It is the module that says signed versus unsigned representation. Okay? So if you have questions about that, it is a good time to review that because this is important in this class. Okay, so my speculation is this program should take this branch because the overflow flag should be a 1, and we should end up over here on that particular halt instruction and not this particular halt instruction. Okay, so what we do is we test it. Okay, so we go to RAM file, and then we say file, download CSV, and save file. We'll put it into the temp folder, joy.csv. Okay, and then we switch back onto the command line and only have to change JMPI to JOI. I'm overwriting the log file. Go back to the spreadsheet, go back to the trace analyzer, and go back to sheet 1. Go to file, import, upload, and this time we choose joy.csv. It should be nope. It's the log file. I uploaded the wrong file. So upload, it is log.tsv. Log.tsv. Same file name as last time, but it's overwritten already. So make sure we replace current sheet, use tab, and say no to convert. Import data. Okay, it's a little bit longer. It's quite a bit longer because we're changing more things in the process. But when you go to analysis, it is a lot simpler, right? So what is it telling us? Well, we have location 0, 0, that's our no op instruction, doesn't do anything particularly exciting. Location 0, 1. Location 0, 1 has a few side effects. For the most part, RAM read is not particularly useful unless you have a load instruction, LD instruction. But what is the effect of executing the instruction at location 0, 1? Register A now get 80 in hexadecimal. Does that make sense to you? Why would A get 80 in hexadecimal? Because it's 128, okay? So we get to the next instruction, which starts at location 0, 3, and B ends up with 0, 1. Does that make sense to you? Okay. What do we do on line? What do we do at location 0, 5? That's our third instruction. That's the compare instruction, CMP AB. Okay, we're comparing register A to register B. So what is the result of subtracting 0, 1 from 80? Okay, I'm just trying to scroll down a little bit here. There we go. So what it says here is overflow becomes a 1. The L flag also becomes a 1 when everything else remains as zeros, because everything starts off as 0, and this only reports a change of the flags. If a flag is not changed in the process, it is not mentioned. Okay, so the C flag is a 0. Does that make sense? If I subtract 0, 0, 0, 0, 0, 0, 0, 1 from 1, 0, 0, 0, 0, 0, 0, 0, and I do not end up with a carry or borrow, does that make sense to you? It should, okay? And if you have to think about it, it's not a bad thing, but you do have to convince yourself that 1 followed by all zeros minus all zeros followed by a single 1 should not give you a borrow. Okay? So the carry flag is a 0. The Z flag is also a 0, which means if you subtract 1 from 1 followed by all zeros, the result is non-zero. Does that make sense to you? Because the actual result of the subtraction is 0 as the most significant bit followed by all 1s as the less significant digits. That's definitely not 0. So that's why the Z flag remains as a 0. The overflow flag, the sign flag is what? I just gave you the answer earlier. The sign flag is a 0 because the most significant bit is a 0. The most significant bit of the result is the sign flag. Okay, so the sign flag is a 0. Overflow flag is a 1. Okay, I just explained why it is a 1. So if you take the exclusive OR between the sign and the overflow flag, that becomes the L flag, and that's why the L flag is also a 1. So is that okay? So this is telling me the compare instruction is giving me this result. Okay, these are the changes because of that. So now we go to 06. 06 is our JOI instruction, which is basically saying jump to whatever the label is, but if and only if the overflow flag is a 1. But the overflow flag is a 1 this time, so as a result, we end up getting to location 09. Location 09 is the second halt instruction, not the first one. How do we know that? It's because if you go to the assembler and you go to, this time you can go for one or the other, but I would still go for the assemble tab. If you look at the second halt instruction, it is in fact at location 09. So this is how you can make use of the trace analyzer in conjunction with the assembler to figure out what is going on in your program. Are we okay so far? Okay, so let's make one minor change to this program so that it doesn't overflow. All right, so we go back to the source tab to make a minor change to the program. by changing one of these two. So if I change K1 to 127, it would not overflow anymore. Because, oh, well, that would definitely not do it. But if I change it to 129, okay. If I change it to 129, it would not overflow anymore. The reason why is because 129, the bit pattern of 129 is having the most significant bit being a 1, a bunch of zeros, and then the least significant bit also being a 1. So if you just can imagine, we have a 1 all the way to the left-hand side, to your left-hand side. We have a 1 all the way to your right-hand side. Everything in the middle are zeros, okay? K2 is 1, which is basically all zeros over here with a 1 all the way over here. So if you do the subtraction, the end result is just 1 over here and everything else being zeros, which translates to negative 107 minus 1 is negative 128. But negative 128 is the most negative value you can represent using an 8-bit signed integer. So we are good. There's no overflow in this case. Is that okay? So we'll go ahead and check it out. Okay, so we now go to the program. Now you don't really have to do this, because the change is so minor. You can just kind of change one of the bytes, in the file. But since we are not using the GUI version, it's a little bit harder to edit the RAM file. You can, it's just a little bit harder to find out what is the location that you're changing. So, just to be sure, we use the same approach here. We go to CSV, we download it as joi.csv, and we replace, go back to the command line, oops, there we go, and then we redo the whole thing, okay? Just an up arrow, because I didn't change the name of any of the files, even though I updated some of those. So once you get this started, it's not too difficult to kind of go through the process. Getting it to start the first time can be kind of, can be a hassle. So we switch back to the tool. We go to the trace analyzer. We go to sheet 1, go to file, import, go to upload, and then we upload the same thing, which is log.tsv. It's a tab separated value file. Replace current sheet, use tab, do not convert, import. Okay, so this is new. And then we go to analyze. We have to double check a few things. Okay, so we get to, we have to scroll up a little bit first. So page up, there we go. So at location 0 is a no op instruction. It doesn't do a single thing. At location 1, it is loading the bit pattern of 81, in hexadecimal into register A. I think we're good there, right? Because 81 is 128 plus 1. Okay, so that works. Location 3 hasn't changed. We're still loading a 1 into register B, and it tells us that register B is updated to 0, 1. And this time when we get to the compare instruction, the result of the compare is only setting the sign flag and also the L flag. Does that make sense to you? First of all, look at the carry flag or the borrow flag. If you subtract 0, blah, 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 all the way just 1, from 1 followed by a bunch of zeros and then a 1, should you get a borrow? No. Okay. Is the result 0? No, because you have, the result is 1 followed by a whole bunch of zeros. So it's non-zero, so the 0 flag is still off, being a 0. So we have carry 0 sign, okay? The sign flag is turned into a 1. Does that make sense? Okay. The overflow flag is a 0 because it doesn't appear here. Does that make sense? Okay. And because the L flag is the exclusive OR between the sign and the overflow flag, does it make sense that the L flag is a 1? Okay, so we double check everything and make sure that they all make sense. And then the next instruction it gets to is now 06 instead of 09. Remember last time it went to 09 after the instruction of at 05, the compare. This time it just goes to the next instruction because overflow flag is a 0. So when the overflow flag is a 0, the JOI instruction just says, sorry, we are not branching to where you want me to branch. We're just continuing with whatever is after the JOI instruction. Are we doing okay with this part here? Yes? Okay. So if you want to have a easier way to understand what is JOI, and the entire family, it is kind of the same thing like this. So if you have a JXI, X being a flag that you want to look at, and then a particular label, I'll just call this label X, label Y, okay? There you go. So if you have something like this, it really is boiling down to, in C and C++, if X is 1, okay, which is kind of redundant, but I'm using that anyway, go to label LY. That's all it is translating to. Is that okay? X being a flag, one of the 5 flags, can be C, Z, S, O, or L, okay? LY is just a label, okay? You don't even have to start with L as a name of a label. It can be anything. But whatever you put here, this instruction has the same meaning as this in C and C++. Are we doing okay so far with this? Yes? Excellent. Okay. So we got about 5 minutes left. So I have just enough time to get started with what we'll be focusing on next week. So this will give you a preview of what we are going to be talking about, which also means it will be helpful if you can read ahead of me a little bit at least, so that you know what we'll be talking about, and those words will not be like completely new. You don't have to fully understand everything, just having a general understanding of the material will be enough. So starting next week, okay, we're basically done with excuse me, von Neumann architecture and memory, and we are now moving on to assembly language programming. This slide here, okay, let me show you what it looks like. Okay, it will tell you basically how compilers work. So I will give you a C statement, okay, and if you have something that is nice looking like this, okay, and in this case C is simply a placeholder for a condition, block 1 is a placeholder for the then branch, and block 2 is a placeholder of the else branch. Okay, so they're not actual statements, they're just placeholders. But this code that is structured looks very nice. Professor Fox, Professor Hermele, and Professor Subseveri will like this kind of code. It translates to something that is ugly using goto, like that. So the question is, well, first of all, does that make sense? From the perspective of, is this piece of code functionally the same as this piece of code? You have to convince yourself first whether they are equivalent or not. Are we good so far? The second thing that you have to kind of go through now is to say, but why? Why are we doing this? See this construct here? Isn't that something that we just talked about? If blah blah go to a label. If you can boil this condition here down to just whether a flag is set or not, then we have the assembly code to do just that. Okay? That is the reason why we are translating well-structured code into non-structured code. This is not structured. It has no curly braces. It has no idea of what is embedded into what. The only thing that is structured or nested is this goto is a part of this conditional statement. Everything else is quote-unquote flat. Is that okay? So we're basically flattening control structures. If this is how conditional statements gets translated, okay, what about loops? Okay, nice looking loop, Mr. Fox will totally approve this, into something that Mr. Fox will totally frown upon. But the question is, are they equivalent? Are they really doing the same thing? So first thing is you have to convince yourself that they are in fact doing exactly the same thing. Okay? Do while loop, kind of the same deal. Do while loop actually is interesting because the flattened version is actually easier to understand. This is the original structured code. This is the flattened version. Okay? So you say, okay, well this is good, but we're still staying with C code. Okay? And also, what about the condition C? Like in this case, this C here is negated over here. What if this C is complex to begin with? What if it is a conjunction of two disjunctions, and then each item in the disjunction is another conjunction, and blah, 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 right? Then what do? Well, we got techniques to do that too. So when you look at section 4 is all about, let's get rid of operators in Boolean operations. If your condition has a negation as the last operation, the outermost operation, you can translate the conditional goto into something like this. Now you say, but that's more complex. Yes, as statements, they are more complex, but the negation operator is gone. Okay? What if we have an or? What if the original condition is an or? Now C and D can be each a very complex expression. I don't care. I only want to look at the last operation. If it's an or, then you can translate it into these two. If it is an and, okay, if the original thing is an and, then we can translate it into something like that. So what I'm doing here is I am using a very boring way, okay, but very structured way to decompose the structure of a program so that it becomes flatter and flatter and flatter. So this process repeats and continue until the condition becomes, oh, we just want to look at whether A is less than B. Because by the time we get to, I just want to know whether A is less than B. Now A and B are just placeholders. They're not referring to the registers. But if we can boil down to just a comparison, then we can eventually use a CMP instruction and then use one of the 5 conditional branches to decide, should we branch that label to that label or not? So we just repeat this process until everything boils down to the point where it cannot boil down any further. Then we can start to translate C code into assembly code. Because everything up to this point can be done in C. You can take your favorite homework assignment in cisp310, 400, or 430. Go through this process until this condition cannot be broken down any further. And you have no structure in the program whatsoever anymore. And they can all be done in C, which means you can still debug that program using a debugger that works in C, like CodeBlocks, like GDB. Okay? When it gets down to the point where none of these rules apply anymore because we don't have operators and or not anymore. We do not have structured code of conditional statement, while loops, or do while loops. At that point, then you can start to translate things into actual assembly code. Is that okay? So the idea is to do as much work as possible while the program remains as a C program, so they can debug it using your favorite tool to debug a C program. When it gets down to the point where we can no longer break it down using these rules any further, then we can start to translate it into assembly code. Is that okay? We are almost out of time. So we do have an example, and you can see that this is basically the end of the module. Okay, when it comes to the concept and the instructions, this is the end of the module. What is the rest? The rest is, well, okay, comparisons a little bit, but the rest of this, or the majority, the bulk of this, is really giving you an example of step by step how we translate things into assembly code. So yes, it is extremely tedious, but that's what you'll be doing for the rest of this semester. So understanding this process is going to be very helpful. Now, if somebody is to ask me, are you really going to give us something like this to begin with and translate all of this into assembly code? The answer is no. I will not give you something like this senseless. I'll give you Fibonacci code, okay? The recursive version of Fibonacci, okay? Yeah, that's fun stuff. Okay, this is boring. So I'll give you fun stuff. Okay, and of course I cannot do that until I have talked about how you implement subroutines. Okay, how you pass parameters, how you return a value, how you deal with pointers, blah 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 blah. But after all of those topics, we'll be able to write Fibonacci recursively using the toy processor. And we'll be able to traverse binary search trees, and we'll be able to follow linked lists, blah, 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 blah. Yeah, we'll be able to do everything that you can imagine in C and C++. It's cool. And I see a few people who came from cisp310 that I taught a year ago. And guess what? You guys are one step ahead because the way I represent the columns in the spreadsheet corresponds to memory locations in this class. So those people already have a basic understanding of how subroutines are implemented in hardware. Okay, we just need a translation of the terms. Now, if you did not take P300 from me, it's okay. I will explain everything from the beginning. Okay, it's just that those people who took P300 from me can look up the notes, okay, especially when they get to subroutines, because that's going to be helpful. And if you want to know how I taught CISP300 a year ago, it's on YouTube. Like everything else, it's on YouTube. So, all right, so I'm going to end today's lecture. We'll go to the lab and get started with this lab.